Good day to everyone. Thank you for taking time out of your schedule to join me today to learn a little bit about how to gain a little more insight into your day-to-day modeling with at risk, and particularly with your inputs. And if you're joining us for the first time, the pace at which we cover the basics will be quite fast. Therefore, I would recommend also taking a look at our on-demand Introduction to Risk Analysis webinar. And that can be found when you go to our palisade.com website. You can click, there's an on-demand section on the right-hand side. That'll take you to a listing of other webinars that are also available. So again, we are recording this, so sit back, absorb the concepts, and feel free to interact via the GoToWebinar question panel there. As you can see on the screen, my name is Michelle Jackson. I am a product manager here at Palisade Corporation. And the only product that we're going to talk about today is At Risk, which is our flagship product. And obviously you've heard about it because you're joining us for the webinar. However, we do have other tools that may interest you, but today we're just going to focus on At Risk. So what is At Risk for those that are brand new to Palisade and you're just checking out this webinar for a first-time exposure to us? Basically, use Monte Carlo simulation to quantify how likely something is to happen, not just that it would happen, but how likely it is to happen. And when we say at risk, it's funny because I heard one of our other presenters mention this. It may actually make you think that you're only going to analyze risk. You're only going to analyze risk, but risk can be positive or negative. So today we're going to focus on the inputs, properly assigning inputs and assigning correlation and possibly copulas to your inputs in order to get a more accurate range of possibilities, which is what At Risk provides for us. What kind of questions does At Risk answer? Many of you already know At Risk answers questions such as what are the chances we'll make money on this venture? What is the probability we'll finish on time or within budget? What is the range of capital reserves necessary to meet our goals? The key questions or words that are in these questions are what are the chances? What is the probability? What is the range? It's not just a single point estimate. It's giving you more information. So what are we looking to achieve during this webinar? Basically, I'm going to give you a brief introduction to At Risk and Monte Carlo simulation. And for those that are very familiar with it, it might be helpful just to see how we introduce At Risk to new folks if you're trying to relay At Risk onto team members that you work with. We're obviously going to cover correlation, what is it, and how to incorporate it in your models. We're going to cover copulas. What are they, and when should you use them? How do we incorporate them into our models? Essentially, when we're working with a risk analysis situation and we're in At Risk, there are 6 steps that we want to think about. The first is going to be exploring the model logic, just thinking about the basics, like what variables are involved and everything. And then we're going to designate the inputs. And it's at this step 2, designating the inputs, that we're going to think about the correlations and how our inputs essentially relate to one another, because that's what correlation is all about, or if they're associated in some way. The next step is going to be designating the outputs. The 4th step is simulating. That's the easiest step of all because At Risk does all the work for you. And then also analyzing results and communicating with others. And today, when we're talking about copulas, I'm going to bring up that communicating with others because copulas is kind of one of those things where people feel like it's really scary to go into, but the reality is once you understand the basics of it, it's not as bad as it first sounds. We'll uncover the mystery today. So what is Monte Carlo simulation? Let's go ahead and go into our Excel worksheet. Monte Carlo simulation essentially is a way to substitute the values that you have as your uncertain inputs, substitute those values with distributions, probability distributions. Then what we do is we draw random samples from those probability distributions and we collect all of the outputs that we've designated, we collect all that information and we show a final output for it. So that's the basics of what Monte Carlo simulation is, but I'm going to walk through those step by step. So this particular very basic model is essentially a a profit equals revenue minus cost model. And what we have is we have the volume, which is uncertain. We don't know exactly how many we're going to sell. The unit price, we may change the price. It may depend on where it's being sold. It might, what deals we have with different companies or what have you. So the price may fluctuate. The unit cost may fluctuate, and the base cost may fluctuate. So those are all uncertain inputs. So I'm going to, just for simplicity's sake, I'm going to leave base case as a static value of 20,000. But the volume, I'm going to replace that volume with just a normal distribution, because most people are familiar with normal distribution. So if we go in here, let's go ahead and define it with a normal distribution, and we are going to say a normal distribution, and let's use cell references. Normal, there, static value 500, that looks good. Say OK. So we've added our input there. Again, if I'm moving along too fast, I encourage you to take a look at our general at-risk webinar. So here we go. We're going to go here, 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 and static value of 200. That looks good. And then the last one that we're going to do is here. We're going to so we're just on step 2, basically defining our inputs. And for this one, instead of the triangular distribution, just to change it up a little bit, I'm going to use the PERT distribution for unit cost, just to show you that at-risk can have different kinds of distributions during any given simulation. So we'll do the PERT. Here, here. Excellent. And then on this is the step where we would do correlation. However, I'm going to do it first without correlation, then we're going to talk about the basics of correlation, then I'm going to come back and we're going to compare the regular simulation that didn't have correlation with the one that does. So our outputs that we're interested in is simply profit, which equals revenue, which is located here in C6, minus cost, which is located here in C10. So let's go ahead and add our output. Click OK. And then add our output here, click OK for profit margin. Okay, so we're going to run a very quick simulation. Let's just do one simulation with 5,000 iterations. So here is our output. Our output shows us that there is approximately a 7% chance that we're going to lose money on this deal. And there's approximately a 7.6% chance that we will exceed 40,000. If we want to check out what it looks like at 30,000, we can go ahead and enter 30,000 here. There's a 21% chance we'll exceed 30,000. So I'm just going to quickly just do it nice and easily, chart this in Excel, so we can just take a look at it afterwards once we add our correlation. So let's just hide that final chart right there. And let's go back and talk about correlation and how it's going to affect what this graph means. And for those that are new to Monte Carlo simulation, the other thing I should point out is that if we have this dice icon turned on, you may not know what just happened during that simulation. So I'm just going to quickly show you that if I turn on that dice icon, essentially what happened is in between, if we look at this defined distribution here, what happened is during every iteration, it picked a random value from here and put it into this cell. It picked a random value from this distribution and put it in this cell, and it picked a random value from this distribution and put it in this cell. And I should probably choose the round. So I just want to make sure that it keeps a whole number here for numbers sold. So this is a good point too, that when we're working in at-risk, we can still use standard Excel functions wrapped around any of our at-risk functions, as well as inside some of our at-risk functions as well. So I just used the round function so that it shows that whole number there. But essentially what happens during an iteration is it randomly draws values from those distributions that we assigned as our unknown inputs, and then it goes through and calculates the total revenue here, the total cost here, and then the profit and the profit margin here. So during an iteration of, during a simulation of 5,000 iterations, it will go through and calculate it 5,000 times. It will randomly draw 5,000 times, and then it will create this output distribution. So maybe when we look at this and we say, oh, there's a 7% chance that we're going to lose money, well, what does our profit margin look like? Let's take a look at that graph, because that's going to be interesting to us. So if the standard is 20% in your industry, we can go ahead and look and say, well, 56% of the time you're not going to hit your 20% profit margin, so this isn't a good deal. So these are ways that you're able to answer your questions with a little more information rather than just taking a single guess at the fact that, yeah, we should earn about $20,000 as the average. So I'm going to turn off that dice icon, and let's talk a little bit about correlation. So the basics of correlation, let me go to our slideshow here. The basics of correlation is that correlation occurs when two or more input distributions are related in some way. And that particular way is when they're linearly related. Correlation is denoted as a value between -1 and 1, and it represents the degree to which the two variables move in a linear relationship to one another. So the values will always be between -1 and 1. So just to help with this concept, I'm going to give you one graphical representation now and then one when we're in the software. The first is this one. This right here is basic +1 correlation. So this shows you that as one variable increases, so does the other. So for example, time exercising and calories burned. Granted, not a perfect one-to-one, +1 correlation. However, there may be a decent amount of correlation, so it might be a 0.7 or a 0.8 depending. But a perfect correlation would mean that these variables move in the same direction at the same exact time. So that is a +1 correlation. Other positive correlations could include temperature with ice cream sales. So as temperature rises, ice cream sales rise. As temperature decreases, ice cream sales decrease, etc. Height and shoe size, salt content or percentage of salt in the water, and buoyancy. There are all different ways that different input variables could be correlated to one another. Here is another example of positive correlation. And I know you might look at this and go, whoa, but the lines are going down. It's still a positive correlation. The two lines relative to one another are moving in the same exact motion. So that's an exact +1 correlation. So although the direction of the lines would imply a negative solution, they are in fact positively correlated, because when one variable increases or decreases, the other one does so at the same time. So think as gas prices go down, the cost of flights will go down. Again, not a perfect correlation, but however, it is a decent amount of correlation. So it would still be like a 0.8, and that it would be on the positive side. How about negative correlation? Here's a representation of two variables that have a negative correlation with one another. So think as interest rates go up, housing sales go down. Other negative correlation, the age of a chicken going up, egg production would go down. Time exercising and body fat. The amount of exercise that you do as it increases goes up, and then the body fat goes down. If you stop exercising, the body fat will increase. Snowfall totals with number of cars on the road. These are all negatively correlated. So the last one is a zero correlation. So this is a representation of zero correlation. So when looking at this, think about how you would want a diversified stock portfolio to look. So you don't, as one goes up, the other one may stay static, but then at least when this one goes up, or when this one goes down, this one is compensated by going up at the same time, so that diversification that you may want to see in your actual portfolio. So this is the basics of correlation. Now let's go into at risk. Here we go. Essentially, in at risk, there are two correlation methods available. You can add basic, or shall we say linear, correlation between two or more input distributions, and you can use that. You can use what's called our defined correlations matrix, which is in this option. So in the at-risk ribbon, the fourth icon in from the left, we have defined correlations, and the drop-down menu there is going to have the correlation matrix, defining Copulas, and fit Copulas. So the first part of today's webinar, we're going to focus on the correlation matrix. So for the previous example, this example right here that we were working with, we could add a correlation of -0.8 for the input variables. So because we figure that as the unit price goes down, as the price goes down, unit price goes down, the number sold may go up. So that would be a negative correlation. So let's go ahead and let's select our first one and select our second one. So those two variables we're going to select, and we're going to define a correlation matrix for it. So when you go into the defined correlation matrix here, we can go ahead and enter 0.8 here in our correlation matrix. If we want to see what that would look like with the scatter plot, we can click on the scatter plot icon down here, and you're going to see what the scatter plot is. Essentially, this scatter plot represents if you were to map the data out, the volume sold versus unit price, this is essentially what you would get, or what you're looking to get with that correlation. And let's go ahead and rerun the simulation once we add this. So I'm going to specify where I want that matrix to go. We're just going to put it right here. We're going to click OK. So now we've got our correlation added in there. Let's go ahead and click OK. So now it puts in our correlation matrix here. So there's our correlation matrix. When it is in the spreadsheet itself, note that you can change the correlation here without having to go back into that dialog. You can edit it here. Also note that you will always have a 1 on the diagonal when you're in a matrix. So as your matrix grows, note that you will always have a 1 on the diagonal. And this, you'll see blank spaces on the other side, and the reason why they're blank is because simply it's to avoid confusion. And the fact of the matter is, if there's a 0.6 here, you can visualize a 0.6 being in this cell. It's a mirror image if you were to fold this matrix over on that one diagonal. So let's go ahead here and say that, and actually let's do a -0.8, okay, instead. So we have a -0.8, and great that I put 0.8 positive in there, but I actually want it negative. So just good to show you that you can enter that right in the spreadsheet itself. So let's go ahead and run that simulation and see what we get. So we kept everything else the same. We're now just going to do the simulation with correlation taken into account. So now how does that affect our output? Well, let's take a look. We have our one to the right that is without correlation and the one with correlation. So now all of a sudden, now that we've taken into the account that while at risk is sampling those random numbers, we want to make sure that it's sensical. So we want to add that -0.8 in there to correlate those to make it make sense, because if the price is, you know, super low, you're probably going to sell more. So we want to so we don't want to necessarily draw a random value for volume sold and have it be low at the same time that unit price is super low as well. So this just allows at risk to draw a more realistic sample, if you may. So here we have now only a 1.8% chance of losing money, only a 6.1% chance of exceeding $30,000. So In the first case, it looked like it was pretty promising. There's 20%, 1 out of every 5 times we're going to end up exceeding $30,000. But here, it's not as promising, but the good news is it's also not as bad on the other tail either. So it depends on where your risk tolerance or your risk threshold is as to whether or not you would proceed in this situation as well. So what if we wanted to overlay these two? We wanted to overlay this graph on top of this graph. Well, what we can do is we can set up what's called a risk sim table. And this can be used, and for those that are new to the software, this is also covered in that introduction to at-risk, the basic webinar. But say someone thought the correlation should be -0.8, someone thought it should be -0.6, and you just want to, just for reference point, want to have it also show me the overlay, the output overlay when there's no correlation. We can actually set up what's called a risk sim table. So you just type in equals risk sim table, and then we're going to select the array of those 3 values. So there's 3 values there. So now we have this risk sim table, and if I look here, it's risk sim table for F8 through H8. What this means is that if I were to run a simulation right now, if I only ran one, it would take the first value, F8, and plug that into this cell, E8. If I ran 2, it would do the first simulation. If I ran 2 simulations, it would do the first simulation with -0.8 and the second simulation with -0.6. And then if I did 3 simulation, it would be with 0. How can I get this to be in here so that we can have that correlation change during each of the simulations? Well, it's as simple as saying equals and then click on that cell. That's it. So you do your own cell reference because you're in Excel. So now when we run this simulation, we're going to see the first simulation will have -0.8 as a correlation, second simulation will have -0.6 as a correlation, third simulation will have 0 as a correlation. All other factors are going to stay the same. So let's go ahead and start that simulation. You're going to see it go through the 3 simulations. And the key fact is when you're running with a risk sim table, you want to make sure that you change the number of simulations to match the number of entries in your risk sim table. So in this case, it's 3. So let's go ahead and start that simulation. So here we have the first one. You can see profit for simulation number 1. So this is when correlation is -0.8. If I go to this little curve here with the number sign on it, that's going to say if I want, I can look at simulation 2 and I can look at simulation 3, or I can show all of them together. And now when we see all of them together, we can see the overlaying of those curves. Now if I want to see the green delimiter up top here, all I have to do is right mouse click, go to graph options, go to delimiters, and change my default to 3. So now we can look, and these values here in the delimiter sliders tell us a better story. Essentially, when we look at it, we can tell that we need to take correlation into account, but the difference between a -0.6 and -0.8 isn't that huge. It's not going to drastically affect our situation. However, if we base our decision on an example where there is no correlation, we may not make the right decision and we may put ourselves in more jeopardy. So this just gives you an easy look at how you can alter the correlation that you want to have in your actual model. And just note that with the correlation, typically your distribution is going to be tighter. It's not going to be as loose. So there'll be a tighter range. So there'll be less effect on the tails of your distribution. So let's take a look here. So basically, as far as the basics of correlation. If you know that your inputs are correlated and you can account for it in your model, you should add that correlation. Essentially, there's no excuse for claiming independence of variables when you know that it isn't realistic. So you want to make sure that you take all those factors. So when we're talking about the 6 steps of modeling, that first step, model logic, is when you want to just start thinking about how things are all tied together. So with that being said, even though two variables may be correlated to one another, it doesn't necessarily mean that there is causation between the two. Certain variables can move together and it may not be known why the movement occurs. Essentially, correlation is a valuable tool, but it can't imply causation because of what statisticians call confounding variables. And confounding variables essentially are variables that affect the relationship between two or more other variables in ways that are typically undetected or immeasurable, such as smoking and lung cancer. That's a good example where there certainly is a correlation, but there are also so many other confounding variables that affect the relationship between the two. So I'm going to take a quick peek at time. I am going to really skim through, but I think it's important. Sometimes it helps to see how something is calculated to better understand where values come from. So I'm going to quickly open up. I'm not going to go through all the calculation, but I am going to at least show you if we were to calculate out our own correlation, which we're not going to do, but here we have two sets of numbers, X and Y. This would essentially be historical data right here. The mathematical way of calculating the correlation is in this text box, and we went through and I did all the math for you and figured out the exact thing, and this is by doing it brute force, this is the correlation that I came up with. However, an easier way to do that would be if we were in Excel, we could just do equals correl and then select the range. So that's this right here up top is the formula that you could use in Excel. However, there's an even easier way. When you're in at risk, you can go to this data viewer, and if you click on data viewer and select your range of variables, range of values here, click OK, and if you notice the correlation coefficient, I'm going to change it to Pearson coefficient just because that is what Excel uses to calculate the correlation. At-risk uses Spearman rank correlation. So let's go ahead and click OK here. Now if I go here, we can see that 0.741, negative 0.741, that correlation value is located right here, which is located right here. But then we also get the visual of the plotting of those points without having to manually plot them. So when we think about correlation, if I go back to this plot of these points and I add a trend line, basically correlation is assigning a value to how loosely or how tight these values these points that are plotted are to the trend line in it. So when we think of correlation, we think of a linear relationship, and that's an important thing to note, that it's the linear relationship between two variables, okay? And just as a preview of what's to come, copulas take care of things when they're not linearly related. So that is where the two coincide together. So that's the basics of how to calculate it. I want to quickly show some examples in at-risk so that you can see. Let me go ahead. Let's go back to our original example. So here we are with our original example. Now, previously we had just these two variables in our matrix. What if we wanted to add unit cost into our matrix? Well, we can do so if we click on that matrix and we say define correlations, correlation matrix. It will bring up that correlation matrix. Now, if you look at the bottom here, there's this add inputs option here. I can say add inputs, and it's going to say which input would you like to add. We're going to go ahead and add the unit cost, which is C8. So we can click OK. And now we have C8 in here as well. Let's go ahead and add negative 0.8 for both the unit price with volume sold and unit cost with volume sold. Okay, so let's go ahead and click out of this one. So we're going to say negative 0.8 for volume sold and unit cost. And we have 0 for this sell price and unit cost. So when we look at this, before we click OK, a good habit to get into is to check the matrix consistency, and you can do so by clicking on this icon here in the bottom left. So if I click on this, I can say check matrix consistency, and it says this matrix is not self-consistent. At-risk can generate the closest self-consistent matrix. Would you like to proceed? So now what it's saying is that this can't be a possible situation. There can't be zero correlation between these two when individually those two are so heavily correlated with a third variable. So it's saying, hey, I'm going to go ahead and recalculate this correlation for you. So if I click yes, I want you to take note of what happens to these negative 0.8s. They will automatically change to a negative 0.7 if you're going to maintain this as a 0. However, if you're adamant about making sure that this particular cell in your correlation matrix stays at a negative 0.8, and maybe you're okay with it varying this particular cell in your matrix, you can actually do what's called enter adjustment weight. So let me go ahead and put this back to negative 0.8. And when I click on it, I'm going to say, and we can put this back to negative 0.8. So when I click on this, I'm going to go ahead and say enter adjustment weight, and I want to give it an adjustment weight value of 100, meaning I want that to stay as close to negative 0.8 as humanly possible when it recalculates the correlation. And then for this one, I'm not as concerned about it, but I would like to have it have a little bit of control. We can enter the adjustment weight here, and you can either enter it in manually or you can choose from the popular options here. So we can say 75. So you're going to see it has this negative 0.8, negative 0.8. Now, if I go ahead in here and say I want it to be lazy, and I said, oh, well, if it's negative 0.8, and I don't want to give any thought about it, and I try to put a negative 0.8 in here, when I go to check the matrix consistency, it's going to give me that error message again. But this time, when it goes to adjust this value, it's going to have to hold this one static and this one change just a little. So we're going to go ahead and say yes. So now you can see this one is close to negative 0.8. This is negative 0.75, so it only changed a little bit. And then this is a positive 0.2. Again, it's basically saying that if two input distributions are each heavily correlated with the third, then by default, those two must have some form of correlation with one another. And to graphically see that, it's not going to have that much form, but there is going to be a little bit of a linear thing, very little, but 0.2 is certainly closer to 0, but there is going to be some association with it. So this just gives us a way of being able to hold things static and tight. So now, if I wanted to run my simulation again, but this time let's first get this in here. So we'll say OK. And it's going to ask, you've entered adjusted weights. Would you like to save this as, you can actually save your weighted one also, so we can save a copy of that weighted one here. So we can see that, and you'll notice that when you populate that correlation matrix, it's going to color those cells to say, hey, the reason why these are red and yellow is because we held those based on those weights that you specified. So now we have this new correlation going on here. So what if we decided to, again, we're not going to We could go through and do 0.8, 0.6, but we don't need to. Right now, this is the matrix that we're going to go with because we did the weighted thing. So we're actually going to ignore the risk sim table here. And you can see here, let's go ahead and put this in as negative 0.8 because I don't want to change that. Okay, I want to keep that one static. So we're going to ignore this. This now is no longer tied to anything. So let's go ahead and run a simulation here. So here we have that same situation, but now we have all of the correlation set in here amongst those input variables. So now we can look and say, okay, there's a 2% chance or 3% chance, 3 out of 10 times we're not going to make money on the deal. About 12% of the time we will exceed 30,000. Let's take a look at what our profit margin looks like. Now we can look at it here and go, oh God, 60% of the time we're not going to hit our typical 20% in our industry, so maybe we shouldn't roll with this. So this is what's going to allow you to have more information when you're making those decisions. So another quick example that I want to do, let's close this out. The next one that we're going to do is going to be, this one actually is from our knowledge base. It's from our knowledge base article. So if you have never visited our knowledge base, you can go to palisade.com and under support, it's I think the second option down on the drop down menu, feel free to just select down and choose knowledge base. This one is a particular one. So this is an example that is going to show us how the article was about how to use instances when working with correlation. So for this example, exchange rates are negatively correlated with interest rates. However, exchange rates in one year aren't correlated with interest rates in the other year. It's just the way that this particular model is set up. So our wish is to use the same correlation matrix for year 1 that we use for year 2. And if we click on cell D12, 13, or 14, you're going to see that we do have a correlation matrix. It's called currency core. And if I look here on this other tab, this is the matrix it's referring to. So what we're saying is we want to use this same matrix here, so negative 0.7, negative 0.5, and positive 0.6 for these 3 values that we want to use, or for these 3 inputs that we want to use for these 3. How do we do that without having to create multiple correlation matrices? So just envision, like, if you're doing a net present value model and you want the inputs to be correlated for year 1, year 2, year 3, year 4, year 5, all the way across, you would have to have 10 matrices. So how do we avoid all that clutter? Well, if the years themselves are not correlated to one another, then you can simply use what's called instances. And the way you can see what an instance looks like is if we go into this matrix, the dialog, the correlation matrix dialog, when we go into this, it's actually going through all of my inputs. So when we go into this, you're going to see this right here, this word instance. This is kind of one of those overlooked words when dealing with correlation. We can say here that if we want to, we can look and we're going to see year 1 didn't have a name assigned to it, and year 2 did. So if we click on year 2, you're going to see that, see how these cells change to E12, E13, E14. So this is showing the different instances. This one is referring to D12, D13, D14. So this is showing year 1. Let's rename that so it's more clear. We can click on this icon right here, which is the rename the instance icon. And we can enter the name here and say year 1 and click OK. So now we have 2 instances of this correlation model. So if we click OK, we can go back into our initial spreadsheet. And when we go back into our original spreadsheet, now we're going to see it has a name here as one of the attributes to the risk core function. We now have year one. So now that's where you know you're going to name the instance of it. So we could easily do year 3, take these values, slide them over. Okay, so we're just copying those same values. And then we could say, I would like to get rid of the instance here. Get rid of the instance here. And get rid of the instance here. Now let's try that again. So define correlations, define correlation matrix. Okay, get my window over here. So I had already added it, so I just have to rename that one to year 3. Okay. There we go. So we're going to see year 3, F12 through F14. We're reusing that same correlation matrix, and we can click OK. Now when we look in the formulas here, we can see year 3 is there, year 2 is there, year 1 is there, but they're all using the same currency correlation matrix, or the matrix that's named that. So the next one I'm going to skip just because I want to get to the other stuff, is essentially about, and I encourage you to feel free to open up your portfolio analysis model in your example spreadsheets. You can go to correlation and copulas, and when you do, if we go to correlation and copulas here, go to the portfolio analysis one. So you can go here and play with some correlation with stock prices there, but I'm going to skip over that because I definitely got to get to the copulas. So the side note about correlation is, be warned that there are times when a strong correlation may not make a great deal of logical sense, so it's important to realize that the meaning of input cells need to be taken into consideration. So there are some situations where 2 input variables may have a correlation with one another. However, logically, it doesn't make any sense, and it could be completely coincidental. For instance, I read in one article somewhere that there was a strong correlation between the population of whales and the stock market. Obviously, when the so in this situation, when the population of whales increased, so did the stock market, and vice versa. Where there was a strong statistical relationship between the two, there certainly was no causal relationship. So the fact that the two increased and decreased in tandem was purely coincidental. So that's enough about correlation. I need to get to copulas, and I am going to try to get through this in 15 minutes flat. So let me just quickly close out of this example file. So let's look here. We can look here, and this going back to the basics. So at the beginning of the webinar, I had shown you how correlation value is calculated, and we looked at the linear relationship between X and Y. So we're going to revisit the same situation. So here are some X and Y values that we have here, and this is what the plot looks like. The value of the correlation that we see here returns a 0.197. Okay, so we really can't really fit a good line to this data. But that doesn't necessarily mean that these values, these 2 instances or these 2 situations don't have or 2 variables don't have a relationship with one another. If we were to expand out that data set and use this data set here, we could insert a scatter plot of these right here. Let's go ahead and insert a scatter plot. So all of a sudden we have a scatter plot. And you may look at this and say, well, there certainly is a relationship. In fact, this relationship is the actual y equals x squared relationship. However, the correlation is 0. Because correlation is linear correlation. It means that we cannot fit a pretty line to this. So what can we use to describe or let at-risk know what kind of relationship these 2 variables have? So when would a situation like this come into play? Well, this may be a situation of angle of light versus light dispersion. Or the inverse of this situation might be where there's little, well, let's actually I'll show you what the inverse, so it's easier to talk about here. Let's do times -1, and let's copy that down. So the inverse of that looks like this. This might be a situation, ignoring the numbers in the graph, just the actual shape of the relationship between these two variables. This may be a situation where when there's little rain, there's little crop yield. As the rain increases, the crop yield increases. However, once it hits a certain tipping point, if the rain continues to increase, the crop yield, which would be on the y-axis, is going to go down. Okay, so there are ways to tell a story between two variables using something other than a line, and that's where copulas come in, where correlation tells the story between two variables when they're linearly related. So stay in line with the climate and rain. Let's go ahead and take a look at an example file that's loaded with your product. Go to correlation and copulas. We can go down here and go to climate copulas. So applications of copulas are often found in finance, but they do appear in other places as well. So this is a situation where it's talking about rainfall. And each observation, the first data set here, represents the average precipitation over a 5 consecutive day period for 2 German cities. Each 5-day period is separated by 2 days from the next 5-day period to essentially reduce autocorrelation. So each variable is highly skewed to the right. So when we map out this variable, it's going to look like this. And when we map out this variable, it's going to look like this. So each one is highly skewed to the right, which means it's well fit by exponential distributions. So I think I can still do quite a bit of it. Let's see if we're willing to hang on and bear with me for 10 more minutes. I can show you how we recreated this. So if we look at this in the data viewer, if we look at these in the data viewer, we can go ahead and take a look and see exactly what we saw in the other graphs, the ones that you saw that were in that worksheet. All we did was we dragged them out and we actually charted them in Excel. So you can see this is that data that's loaded there. Then if we look at the scatter plots of these, this is the pattern that it's showing. So it's really heavily associated and concentrated here and a little looser out on the tails, but it's not fanned out. So we need to find something that fits this style correlation, where before it was, let's see if we can fit a line to it. Okay, so let's go ahead and do a regular correlation and then a copula fitting to this. So how do we do a regular correlation to this? We will actually, we did a distribution fitting, so let's go ahead and do a batch fit of these two examples. When you're doing distribution fitting, and this is covered in the basic one, we can say this situation, we know that 0 precipitation is the lowest possible value. So we know that out of the distributions we're going to choose to try to fit, we're going to do the fixed bound. Now, I'm not going to go through and select different ones. We're just going to roll with the defaults here. So it is going through and it is going to fit those two variables. And when we look here, what it does is it also provides us the linear correlation. So you can see here that the linear correlation in this report that's produced when we do that batch fitting shows it has a 0.859 correlation. Okay, so let's take a look at what that function looks like. It's basically, this is for Berlin. So Berlin, Potsdam. We'll paste that in, and then we're going to go back to that other worksheet and copy this guy, Control C, and paste it in here. Now if you notice, it doesn't look right. All we have to do is we have to add an equal sign here, and then that will put in that value, and that will make it an input. So now there's our two inputs, and I'm going to go ahead and copy this again down here. So these are our two input distributions, and you could use these in any of your models anywhere. Now if we wanted to assign a correlation to these two inputs, if we were going to run a simulation and use these inputs with an output, we could say define correlation matrix like we did before, and it'll come up here, and we're going to say, was it a 859.859? Click OK, because we pulled that from that other worksheet. We're going to select a location for that matrix, let's say here, right on the side of it. So this is what our correlation matrix looks like. Now, what would this look like for a copula? What if we want to fit a copula to this? So we can click in the data here. So the actual data, not the input distribution, but the actual data. So click in the data here, and then select Define Correlations, Fit Copula. And it's going to say, just like you saw in that distribution fitting, it's going to say, well, which of the different types of copulas do you want to fit? And you can choose which ones you want to fit. In this situation, we're just going to try fitting all of them and see which one comes out the best. So here we have the data plotted against each other, and you can see that in blue. And then the red is the different distribution. So if we chose the Gaussian one, it's going to look like this. If we chose the Gumbel R, it's going to look like this. So we're trying to find a scatter plot representing a copula that is similar to the scatter plot that represents the data. And with values using the Kaike criterion test, we can come up with the best fit based on actual values. And this one, it's saying the Gumbel one is the best fit. Another fun thing to do is to take this delimiter, and the delimiter slider, and you can see now, you can see that with the data itself, the blue, it's really tight on those tails. So what's important to us is that we want to find a distribution that fits tight on those tails. So you can see here the numbers 9.6 and 9.7 match each other quite nicely on the tails there, and also on the tails up here. You can see 10.5, 10.8. If we had used Clayton, it would look like this. This is off by 1.5%, and if we go up here, wow, it's off by 5% versus being nice and tight. So it's showing you that the Clayton is more of a fan where it's tight in the corner and then loose out on the sides. So instead, we're going to want to stick with the Gumbel. So just like you do when you're doing distribution fitting, you click on the one that you want to choose, and you say Write to Spreadsheet. And it's going to say, do you want to create an unattached copula, or do you want to attach the copula to all at-risk distribution functions in a specified range? In this case, let's attach it to those inputs that we have here. We're going to attach it here, and you're going to see that the formula for them will change. So let's go ahead and click OK, and let's write that cell here. It's going to put that same thing there, and we can close here. So when we look here, now we can see that it's a risk copula using copula 3 in the first instance of it. So that's what this is here. So if we want to, we can now go in here and say, take a look at it just like we would with defined correlations. So now this is what it looks like. So this is showing us a little better view of what that copula is looking like. So this is the one that we're going to fit to it. So if we were to run a simulation on this, let's click OK here. If we were to run a simulation, it's going to seem weird because we're going to run a simulation, there are no outputs. We're not going to look at an output distribution, but I am going to show you the resulting correlation scatter plots that come about, because basically what it'll do is it'll show us where the different samples were correlated from. So now if we look, we could do a scatter plot of these two items here. Oops, I actually did the wrong ones here. Hold on. Let's do a scatter plot. Results, scatter plot. So here's the scatter plot with the regular correlation, and here is a scatter plot of the copula. So you can see with the regular correlation, and I should make this bigger so that you can see it, it's more spread out, and it might be hard to see visually, but it's more spread out over here versus here where it's a little tighter. So you can see it's tighter, and it's tighter even on this end, which better represents what exists in the actual sample of the data set. So that's just one other way. The last thing I will say is that you can actually assign copulas just like you would distributions. And I know we saw that if I click on here, say define copula, I just want to cover the fact that there are different types of copulas. There are essentially three categories of copulas, and those three categories are Archimedean, which are the Clayton, Gumbel, and Frank. And if we were going to define, say we decided not to use the suggested one, if we wanted to look at a Clayton one, this is Clayton, this is Gumbel, and this is Frank. Okay? These are all, they all require just one parameter. And you'll see that right here. They all require just one parameter. And this parameter controls the degree of correlation among all the variables. So Everest supports three types of these Archimedean ones, and those are the Clayton, Gumbel, and Frank. That's one category. And if we change the different values here, like say we put a 7 in here, you're going to see it'll change the shape of these. If I put a, you'll see it'll get tighter as that parameter, it'll get tighter and skinnier here and fan out later on in this particular one. Now, if you want to, there's also the other types that are in here. You're going to see an R, Clayton R, that's the reflection of it. The Rx is going to be about the x-axis, and the RY is going to be about the y-axis. So you can see the different styles of the same copula just by choosing different selections there. And let's go ahead and make this a more reasonable. There we go. So the other type is the elliptical style, and the elliptical style of it is your t-distribution and your Gaussian. And when you use the t-distribution and Gaussian, which is here, just so you know, Gaussian is our standard one. And it's hard to tell because we're using these exponential input functions, so you can't tell that this is an elliptical one. But know that the elliptical ones are the Gaussian and the T one. And a nice example of that I will show you is going to be in one of our example files, and I'll quickly show you that. The other example is going to be the empirical one. I'm going to show you empirical right now because we have the example file open. Let's go back to our basic example here. If I were to take these values, I'm going to copy them. Oops, and put them in here. If I wanted to do an empirical, so say I want to say define a correlation, define a copula. I'm going to define a copula. If I can get my, okay, we're going to define the copula, and we're going to use the empirical one. It's going to say select the Excel range containing the empirical source data. If we choose this and click OK, and then it helps if I have my inputs. Let's add my inputs. It will actually create that parabola that we saw earlier, it'll create that, and that empirical is essentially using the data that you have. So that's another way that you can add that empirical data in there. So the last thing I want to show you out of it, if I can put this in here quickly, and it's hard to see again because we have these exponential ones here. If I had changed this to like a risk normal function, it will show up with the parabola that we had seen in that basic example. So just know that there's different ways to represent the correlation besides just with a line, and that's where copulas come into play. So if you need more information on any of the copulas, I encourage you to visit, when you open up your defined copula window, when you visit this question mark, it'll take you right to the different copulas here and explain to you what the different ones are and when they're typically used. So that may be of use to you. Another item that will be of use to you is under example spreadsheets. We also have this stock portfolio comparison. There we go. This one, the option portfolio comparison one. This shows you a situation where you can see after you run a simulation, so let's just do 5,000 just to keep it nice and short and sweet. It's going to actually show you a simulation with a t-copula versus a correlation, a regular correlation. So it's going to go through, and you can see that the correlation table is huge, and the t-table is going to be equally as huge. Granted, the copulas that you saw today were just ones that had one parameter for the most part, but if I close this out and I scroll down, you're going to see that this first one is the correlation matrix. This second one is the t-copula. So you can see T right here, that's the t-copula. And that is a great huge matrix. But what's important to see is that the mean's not going to change. It's still the same values. It's still the same random values. It's just how they're associated with one another. So the mean stays the same, and in this situation, the lower tail is pretty close to one another. You can see here the percentile, the lower percentile is pretty close, but the upside, the winning end of things, the top end of the tail, has a better upswing when you're using this t-copula, and that better represents a situation that captures extreme dependence where two or more stock returns are simultaneously extreme, and that's why the financial industry uses that, especially in the stock markets. So I think this is about where I have to stop. Excellent. And John, you mentioned that when you turn on the random recalc, it seems to ignore any defined correlations. Basically, the random recalc, what that does is that just shows a situation, an individual random draw. The way correlation is actually calculated, and this is something I'll have to add in the next time I do this particular webinar, the way correlation is actually done within at-risk. So you're right, when you're just doing that random one, and that's just for demonstration purposes to see that things are recalculated properly. You're right, it's going to ignore that correlation factor because the correlation actually takes place during a bulk simulation. And what I mean by that is if you have 1,000 iterations, what it's going to do is it's going to draw 1,000 values of the X variable, 1,000 values of the Y variable, sort them, create a rank, and then correlate based on the rank of them. So you're right that when you do that random recalc, it will ignore correlation because technically it's a sample of one. So the rank is one. So, and there is only one. So there's no way to, it's the best fit because there's only one value that it's fitting. So in that situation, you're right, correlation would be ignored, and that's a great point, and I appreciate you pointing that out so that I can put that in the future webinars as well. Excellent. Well, it looks like tornado graphs and sensitivity analysis is of interest. For those that want at-risk for project management, I encourage you to also visit our on-demand webpage so that you can check that out as well. I appreciate everyone's time today. Thank you very much. and have a splendid day.